Have just seen me type condensed version, and I did that because first, as you know, I have no idea when the class ends, and second, I just want to make sure that I give you enough information so that you can work on the homework, which is on page 3. There are these 2 conceptual questions to try to answer, and then on page 4 there are 3 problems to do. So 1, 2, and 3, and to do that, let's see, we definitely need to go over this problem solving strategy, so we're going to get to that for sure. We definitely need to do Newton's second law. We definitely need to go over the definition of weight. Some of this other stuff I might skip for now, though. So, net force. Net force is like the resultant, and I'm sort of feeling silly for not having used the word net. Whenever I was talking about the resultant earlier on this year, I could have said, you have this velocity and this velocity, and you add them together and you get a net velocity. But I've just always called that the resultant. So the net and resultant mean pretty much the same thing. It's what you get when you add up a bunch of vectors. So the definition of a net force is the vector sum, meaning head to tail addition sum of all of the force vectors, all the forces. The vectors just represent the forces acting, bless you, on, and I realize I don't have to bless anybody. Emilio's got it in here, acting on an object. So Emilio, I may just step back and let you bless people. You can be the physics priest. Yeah, sure, you can all bless. Oh, you mean forces? Okay. We could have a whole class of physics priests if you want. So, yeah. So in this situation, there are 4 forces. It's not just 2. There's a 2 Newton force pulling up on this, a 2 Newton force pulling down on it, pulling or pushing, you can't really tell. And there's a 5 Newton force exerted to the right and a 3 Newton force exerted to the left. And it would be a weird head to tail diagram because the vectors would be on top of one another. But guess what I get if I add them all up? How many newtons? Don't say 16. So it's 2, yes. 2 which way? To the right. So you can look at the y dimension and the x dimension and first say we've got a positive 2 and a negative 2. So in the y dimension they cancel. And in the x dimension we've got a positive 5 and a negative 3. So if you add positive 5 to a negative 3, you get positive 2. And you could do a head-to-tail diagram, but it would look funny because they'd be on top of one another. So the net force, that's the summation symbol, and it's used a lot for net force. Sometimes you'll see people write F net, and sometimes I do that if I can't type the symbol. So it's 2 newtons to the right. Or actually, I'll just do, 2 newtons rightward here would be a good way to answer this. Or you could have an arrow showing 2 newtons to the right. So that's the answer to this next question. What's the net force acting on the box? Now there's a weird term. Has anybody ever heard of normal force before? Okay, Max. So not many of you. It's just a specific word, name for a force that's exerted by a surface outward and perpendicular. So I'm going to write my definition of it. It's a force exerted perpendicularly outward by a surface. A force exerted perpendicularly outward. And that's not really that important for today, but we should do it because it's going to come up soon. I'm going to be using that. By a surface. So this, if you look at this box here, if you imagine that's a real box and those are real forces acting on it, the 5 Newton force might be somebody pulling the box to the right. And the 3 Newton force, this could be a tug of war, or it could be the wind blowing it to the left. So maybe there's wind blowing this way, and somebody's got a rope here, and they're pulling this way. And try to get that back. And it's going to end up going to the right because the person's pulling with a force stronger than the wind. But there are these other 2 forces, and if this were a real box, what do you think the 2 Newton force downward would probably be? Gravity, yeah. So the weight of the box. Weight's another word for the force of gravity acting on something. Now the 2 Newton force is the normal force. So if this mouse is sitting on my desk, the reason it doesn't move up or down is because there's no net force acting on it. There's gravity pulling it down, but the desk is pulling it up and they're equal. So there's no net force, so it doesn't go anywhere. All right. Newton's first law seems like it should be really important since since it's the first law. And it seems like it's not something you shouldn't skip. But I think for now, I think we could actually just skip it. So let's skip it, and then we'll come back to it tomorrow. It's the law of inertia. All these warm-up things I've been doing have been related to inertia. And I'm just going to jump in right here. The basic metric unit of force. So if my 2 fingers are pushing one another, if I wanted to measure how hard they're pushing, what unit would I use in a physics class? A Newton. So it's a Newton. And a Newton, 1 Newton, capital N, is about 0.224 pounds. So a little less than a quarter of a pound. And some things that are about a quarter of a pound are an average banana, apparently. We were trying to find things a quarter of a pound. I used to use an example of a raw hamburger patty. If you imagine lifting a raw hamburger patty in your hand, that's about a Newton of force that you would have to use to hold it up. Yeah, Ken?
Is there any relationship between the 0.224
and 2.24 meters? I don't think so.
Oh, yeah.
No. It's just other than similar numbers. So definition of mass. All right, I guess we should define mass. None of you have been in my earth science class, but if I define mass in my earth science class, I say that it's stuff. Because if you look up a non-physics definition of mass, what you might get is the amount of matter in an object. And if you look up matter, what you might get is anything that has mass and takes up space. So it's the circular definition. So mass is really a measure of the amount of stuff in an object. But for physics purposes, it's a measure of inertia. And now I'm feeling like maybe that decision to not define inertia was a bad one. So let's go up to the top. Inertia. If I have a lot of inertia, how can you actually figure out? Let's say you have a box and you're out in space and somebody gives you this box or gestures to it and say, figure out if that box has a lot of inertia or little inertia. What could you do? You could push it. And how would you know? If it had a lot of inertia, what would happen? Nothing would happen. Something would happen. You would move backward and it would move very little. And if it had very little inertia, it would move a lot and you would move very little. So inertia is a resistance to acceleration. That's maybe one definition. And what kinds of things have are most resistant to acceleration? Large heavy objects, so massive things like trains. And if they're, a train, if it's not moving and you try to get it moving, you try to accelerate it, it's very difficult. It resists it. And if it is moving and you try to slow it down, you try to negatively accelerate it, it resists that too. Things like feathers, they have very little inertia. You can accelerate them very easily. So a definition of mass is a measure of inertia. The more mass you have, the more inertia you have. They're really tied to one another. Again, kind of circularly. The unit we're going to be using for mass, what's that one? Grams is I guess the base unit, but the one we're going to use the most is kilograms. Well, is the SI unit, the base unit is still gram, but just the one we use most commonly is kilogram. They're both SI, and it's abbreviated kg. And a kilogram, can anybody tell me something that's about a kilogram? If you,
1,000 grams.
Yes, thank you. But a thing that has a mass of about 1,000 grams. What's it?
Like 2.2 pounds.
2.2 pounds, yes.
Okay, what's 2.2 pounds?
But what's the thing that's 2.2? I used to use a brick. I used to say it's like a brick, but bricks are actually quite a bit more massive than that.
2.2 pounds on that.
So it's a a full Nalgene bottle. So, lots of people drink water out of those Nalgene bottles, 1 liter bottle. This is a 1 liter bottle. So 1 liter of water is 1 liter of water is a kilogram, because a liter of water is 1,000 milliliters, and the mass of a milliliter of water is a gram. So if you want to imagine what a kilogram's like, imagine picking up a full one of the. Anybody have one right now?
Yeah, right.
Yeah. So, there's one. That's a good one. The metal ones probably are a little bit more, but that size water bottle is about a kilogram. Okay, weight. Weight is the force of gravity. And I used to say the force of gravity acting on an object, but I want to say the force of, I've changed it. Force of gravity, um, ding, exerted on an object, usually by a planet. So the reason I add that little parenthetical caveat on there is, you're sitting across the row from somebody, your mass and their mass are exerting gravitational pull on one another, but I wouldn't call that weight. That wouldn't be your weight is not defined by how strongly you're being pulled toward the person in the seat next to you. It's the force of the earth on you. Okay, now we skipped Newton's second law. That's okay. We'll come back to it now. I've been writing this over and over. Newton's second law is F equals ma. And it's really important to note that this, bless you, this F here is net force. So people get into trouble because they'll find some individual force acting on something, and then they'll plug in the thing's mass and they'll try to find the acceleration. But that doesn't really work, because you have to take into account all the individual forces. So that's mass, and you know what A stands for, but I'll write it out. There's Newton's second law. That's probably that, and the third law. Second law is going to be the biggest one factoring into this unit. Third law comes next. First law is kind of an afterthought. So the problem solving strategy, I kind of want to add as a next step, but I think I'll just add it as the first step. So the first is draw a diagram showing all of the forces. What time do we leave? Okay, we're good. Acting on an object. That's the first thing. Draw the diagram. And that it's key that just the ones that are acting on the object. Sometimes it's hard to tell in the beginning, is this a force acting on the thing, or is this a force exerted by the thing? And it can be confusing. The second is to write an equation using Newton's second law, F equals ma. So you have all these forces acting on an object. And from those forces, you can arrive at a net force. And then you could set that net force equal to mass times acceleration. And then write an equation. It's going to be two equations, just a little system of equations usually. Write an equation for the sum of all of the individual forces. What I'm talking about there is the net force. And maybe I didn't say it very well, but so there are two ways to get a net force. One is just to say, oh, it's mass times acceleration. The other way to get a net force is to say the net force is the sum of all the individual forces. And then number 4, if we had another final step, it would be basically to solve. But I think that's an important, that's sort of a given in anyone. So you're going to have a diagram, 2 equations, and then based on those 2 equations, you can solve stuff. Can I flip over? We'll try it. So this is a very simple explanation or simple problem, but it's okay. A 1,200 kilogram car is being acted upon by two forces. There are going to be more forces in my diagram. The car's motor is providing a 1,000 Newton rightward force. Ooh. And friction is providing a 300 Newton leftward force. I'm hating this problem. It's my own problem. So I'll explain why I hate this as we go. All right. So first off, I hate it because I'm going to draw more than two forces. There are more than two forces acting on the car. And second, as we're gonna talk, we haven't gotten to Newton's third law yet. So it's not really the motor that pushes the car to the right, because you can't push yourself. Anybody wants to try it? See if you can push yourself across the room right now. Just put your hand in your rib cage and push yourself. See how far you can go. You can't do it. So in order to push yourself, what you have to do, if you want to actually move across the room, what do you have to push? You have to push the floor. First you stand up, and then if you want to go over there, you push the floor this way, and that pushes you across the other way. So equal and opposite action and reaction. But just to keep things simple in the moment, instead of saying the road is pushing the car to the right, I'm just going to draw motor, and I'm going to write 1,000 newtons. So it's getting 1,000 newtons of force exerted to the right, and sort of the source of that's the motor. But the way the motor does it is by turning the wheels, and the wheels push the road to the left, and the road is really what's pushing it to the right. And then there's this other one. There's friction in the axles, or friction somewhere. You don't have to have your arrows proportional. 300 newtons, and that's the friction. And those are the two forces. But there are other forces. What other force is acting on the car?
Gravity.
Gravity. Which way is gravity pulling? Down. And I'm just going to call that weight. Ooh, that just reminded me of something. We forgot. I skipped something with weight. Doesn't matter for this question. And so if these were the three forces and I added them up, would the car start to accelerate to the right or to the right and down?
Right and down.
Right and down, because if you add these three vectors together, 1,000 is stronger than 300, but then there's also this downward force, so it's going to move this way. But the car doesn't. It goes this way. It doesn't go down. So that tells us what? There's another force. There's another force, which is the normal force. So I'm not going to include the normal force in my math here, but maybe I'll just put a little note that in this case, the normal force equals the weight. So there are two unbalanced forces. The normal force and the weight kind of don't count because they're balanced. So that's how I can get away with calling this two forces. Right. So that's my first step. I've got my picture with all the forces. Now I'm going to use Newton's second law. Net force equals ma. Can I figure out the net force here? Can you tell what the net force is? How many newtons and which way? 700 to the right. So I'm going to write plus 700 equals, do we know the mass of the car? Yeah, 1,200 times A. Well, yeah. So if you want to find the acceleration, it's just 700 newtons over 1,200 kilograms. And lo and behold, when you divide newtons by kilograms, guess what units you get?
Really special.
We're solving for acceleration. Meters per second squared. Really?
Cool.
So let me do that.
Maybe there is correlation.
Yeah, right.
0.583 meters per second squared. Yeah. So how does that work out? Well, so I'm going to give you kind of a circular answer here. if we put in, let me just play with this formula up here. Acceleration is, so mass is in kilograms. That's the unit for mass. The unit for acceleration is meters per second squared. And the unit for force is newtons. But this is one of those kind of bundled units. It has just been decided that instead of calling the unit of force a kilogram meter per second squared, we just rename that a newton. It's like, I'm trying to think of another example.
Oh, so if you're dividing by
I'm blanking on this, but there are other circumstances where you just have something that's complicated and then we just have a very specific name for it, so we don't have to use that all the time. So that's why it works out that way, because a newton really is a kilogram meter divided by second squared. So I drew my picture, I wrote one equation, and then we were done, and I told you we were going to have to draw the picture and write two equations. Well, I could spend some time showing you how we kind of did the two equations here, but let's just say sometimes you don't need to go through all three steps. I think we will need to on this next one. But before we do this, let's go back to the thing I skipped, which was, oh, I see what happened. Over the years, it just got lost. So we're going to have to write this over on the side. So where weight is, right here, weight's the force of gravity exerted on an object. And since net force equals mass times acceleration, for weight, which is the force of gravity, you'd multiply something's mass times the acceleration of gravity. And what is the acceleration of gravity? What symbol would I use for that? G. So this is the formula for weight. Weight is mg. We're going to need that in just a moment. Okay, so bowling ball is sitting motionless on the ground. I'm going to go kind of fast so I can get the test handed out. Here's the bowling ball. The ground is applying a 49 Newton upward force, and it's sitting motionless. What's the bowling ball's mass? All right. We can do this. So my diagram's not complete. So I'm trying to think about the best way to lead you through this. We could say, what's missing? Yeah, we know the weight. So we're kind of jumping ahead though. How do you know the weight?
right?
No,
No,
that's not how we know the weight.
Normal force is weight.
Yes. So let's hold that and let's just go on and do the newtons. Let's do this. Net force equals ma. Of this, what do we know without a doubt? F, M, or A? We know A. So this is going to be 0, and therefore m times 0 is 0. So I'm just going to write net force equals m times 0. So therefore, the net force equals 0. All right, this is how it's supposed to work out. So we have our first equation. And so when you get this equation and you look at this and there's one force and it says the net force is 0, there's clearly something wrong. We must be missing some forces. So that would prompt you to go looking for the other force. In order for the net force to be 0, we need another force going which way? Down, this one. And that would be the force of gravity. That's the weight. So now I'm going to do my second equation where I say the net force equals the sum of the forces. How many forces do I have acting on this? 2. And this force right here, the normal force, is it positive or negative?
Positive.
Yeah, 49. And this is going to be negative minus the weight. And I know from here that the net force is 0, so I can combine these two equations and I can say 0 equals 49 minus the weight. So the weight has to equal what? 49 newtons. So this is 49 newtons. So I've kind of exhausted this process. I've drawn a picture. I've written my first equation with Newton's second law. I've written my second equation where I add the individual forces, and then I set this equation and this equation equal to one another. That's what you do over and over. But now I want to get the mass. So we can use this. Weight equals mg, and the weight is 49 newtons, and the mass is what we're looking for, and g is 9.8. So 49 divided by 9.8 is the mass, and that would be, isn't that 5?
Yep.
5 kilograms. Okay, so see what you can make of the homework. I mean, just give it a shot. I think I've got the answers on my website, but try the conceptual questions 1 and 2, and then look at the answers afterward, and then do the problems 1, 2, and 3 to the best of your ability. I think you'll be able to do those, and if not, we'll